So, friends, let us continue with the discussions on plane non-orthogonal structural members. This is lecture 14 on module 1, where we will explain and continue to discuss about solving non-orthogonal structural members. We already said that k bar of the ith member can be given by T transpose of the ith member, k local of the ith member and T of the ith member, where k bar is the stiffness matrix of ith member in the reference axis system. Okay. Hence, the conventional expression m bar I will be equal to k bar I of delta bar I is also valid, where all of them are being expressed in the reference axis system. Okay. So, we already have this expression where T transpose or T of arbitrarily oriented member for all the 6 degrees is given by this. And T matrix, that is the transformation matrix, is also known to us, which is interchange of these rows and columns. And the K matrix of local for 6 degrees of freedom, namely P, Q, R, S, T and H, is also known to us. Is it not? So, I hope you will be able to fill up the remaining values by looking at this, except that in the last case is going to be AE by L minus AE by L, AE by L and AE by L. Now, look at this expression. If you want to find K global, I have to do T transpose pre multiplier to my Ki and then post multiply this with the transformation matrix. I have all the 3 here. I think you can do a simple arithmetics and try to find k bar as an interesting exercise for any ith matrix. Okay? There is no difficulty in getting this. Once we get k bar, then we know the following equations are valid. K of delta is joint load plus restraints, call this as equation 1. K u that is unrestrained degree of delta u will be again valid with delta u, JLU and KRU with delta u is again minus JLR will give you the end moments and shear of the given member. Okay. Let us now find out what are those important steps which make the analysis of non-orthogonal structures special. Okay. Let us see this. First step could be choosing the jth end of a member will position the xm ym axis of the member. Okay. How to choose this? We already have an idea. Origin of the axis xm ym is at jth end. Okay. Xm axis should be oriented, okay, towards kth end, making length of the member in the positive side of xm, okay, and ym axis is 90 degrees anti-clockwise to xm. That is how you will choose this. So, now this will fix the kth end. Okay. So, for the given member xm ym is fixed. Okay. Now, locate position of the reference axis, that is xy. Okay. Now, find theta, which is the anti-clockwise angle between xy and xm ym. Friends, let us elaborate this. This is my xm ym of a given member. Okay. Let us say this is my xm and ym of a given member, and let us say this is my xy axis of the whole structure. I am looking for the angle theta, which is anti-clockwise inclination of xm with respect to x. Okay. The next step could be, since theta is known, okay, find Cx and Cy and determine the transformation matrix T for each member. Okay. After that, choose unrestrained displacements both translational and rotational. Okay. As first group, then choose restrained displacements. As second group. Friends, when we do this, we have to do an important step here. We have to take care that the unrestrained and restrained degrees of freedom are chosen with respect to the reference axis. I will explain this with a problem. So, I should write here not with respect to local xm ym axis. That is very important step. Okay. Let us explain this with an example. Let us take a problem very quickly, just explain this. I have got a frame which has non-orthogonal members as you see here. Okay. Now, I want to mark the reference axis exactly here, x y axis. Now, I want to mark the degrees of freedom, right. So, labeling is different, but degrees of freedom alone let us discuss. So, I am marking the unrestrained degrees. So, 1, okay, 2 and let us say 3, 4, 5, 6, 7, 8 and 9. The restrained degrees could be 10, 11, 12, 13, 14 and 15. So, we have got to group the unrestrained degrees first and then the restrained degree labels. While marking them, please note my x and y displacements which are unrestrained displacements and restrained displacements are all oriented with reference to the reference axis, but not with reference to the local xm or ym axis. Okay? It is very important. So, you must choose the unrestrained and restrained degrees of freedom in such a manner that they are marked with respect to the reference axis. Okay? That is how it is done. Joint loads should be computed. Okay. Again, you should compute the joint loads with respect to reference axis. So, you know, joint loads are actually reversal of sign of the fixed end moments. So, fixed end moments of any ith member of bar, that is global, will be actually T transpose of the ith member of fixed end moment of the ith member. Let us call this equation number 4. Okay. Now, for our understanding, let us recollect fixed end moment of the ith member is simply for the values of P, Q, R, S, T and H. So, I should say this is going to be M, maybe M A, M B, V A, V B, H A and H B. Okay. So, that is how we can compute for each member. Let us try to explain this in a graphical form. Let us make two statements. I am drawing them individually, they are parallel, okay, of the same length. One is for the local axis, other is the reference axis. Okay. We know this is my jth end, this is my kth end, because the member should be oriented towards the positive side of x m and y m should be 90 degrees to x m. Okay. So, I want to mark the degrees of freedom. Let us say this is going to be my M P, okay. This is my M Q, that is the moments. This is my V R, this is my V S and this is going to be my H T and this is my H H. Please note the degrees of freedom in x m y m axis are marked parallel and normal to this axis. When I move this to the global axis system, then I mark in a different manner. This is going to be my M bar P, this is my M bar Q, M bar refers to the reference axis. Okay. This is going to be my V bar R and V bar S, okay. And this is going to be my H bar T and H bar H. Please note the sign conventions of these, they are related to this axis. Please note the sign conventions of these, they are related to these two axes. So, there is a difference. Okay. Now, if I say FEM of the local, which can be simply MP, MQ, VR, VS, HT and HH. If I say FEM bar of the ith member, then that should be equal to M bar P, M bar Q, V bar R, V bar S, H bar T and H bar H. Okay. Now, FEM bar actually is the transformed value of FEM. So, therefore, the fixed end moments bar is the transformed FEM vector of the member in the reference axis. How to get this? We already gave this equation. Let us once again write the equation, there is no problem. FEM in the global of the ith member will be given by T transpose of the ith member of FEM of local. So, I can get FEM bar now. Once I get FEM bar, reverse the sign of FEM bar to get the joint load. Okay. So, now I can get joint load bar of every member, but I want the joint load of the entire structure. Once I get this, then the end moments m I of the member will be equal to the k local of the member multiplied by delta I of the member plus fixed end moment vector of the ith member. Whereas, I can expand this and write going to be m p, m q, p r, v s, h t, h h will be actually equal to the k matrix of the ith member in local multiplied by delta of the ith member plus fixed end moments of the ith member. Okay. But I am not interested in knowing m, I want to know m bar. So, m bar vector of the ith member is given by k bar vector matrix of the ith member multiplied by delta bar of the ith member plus fixed end moments of the ith member. Okay. It is very easy to get the end reactions of the member as m bar p, m bar q, v bar r, v bar s, h bar t and h bar h. Okay. I can get this. So, now we have to apply this discussion to a specific problem and solve the problem using non-orthogonal matrix knowledge and try to find out this problem.